In this video, we solve problem 8.2.13-T from Essentials of Statistics, 6th edition by Mario Triola. The problem statement says, suppose 233 subjects are treated with a drug that is used to treat pain, and 52 of them develop nausea. Use a 0.10 significance level to test the claim that more than 20% of users develop nausea. Now notice that this time we are not asked to use a normal approximation to the binomial distribution, but we could use a normal approximation to the binomial distribution. And we have every reason to believe that this sample is a simple random sample. It is a binomial distribution. We've got a fixed number of trials, 233. Each patient either develops nausea or they don't. That is completely independent of whether any of the other patients develop nausea, so each trial is independent, and we have every reason to believe that the probability of success in one trial is the same from trial to trial. So since all of that is true, and the expected number of successes, where success is the number of people who develop nausea, would be 20% of 233, and the expected number of failures would be 80% of 233. We see that both of those are greater than 5, so the normal approximation to the binomial distribution would be appropriate here. But I think I'd like to practice using that binomial probability distribution, doing that exact method. So I'm going to use this opportunity to use the exact method. Now hopefully that's what MyLab Statistics wants. We'll see pretty shortly if it accepts the p-values that we get using the exact method. Okay, so the first thing we're asked to do is identify the null and alternative hypotheses. In order to do that, I'm going to share my paper with you. So we look for the claim. It says we're testing the claim that more than 20% of users develop nausea. So the first thing we do is write down that claim. And that means our proportion is greater than 20%. Or typically we write that proportion in decimal form as 0.20. That's the claim. And if that's not true, if p is not greater than 0.20, p would have to be less than or equal to 0.20. Now the one of these that does not contain the condition of equality is the alternative hypothesis. So our alternative hypothesis is this one, because this says less than or equal to. This does contain the condition of equality, this one doesn't. So our our alternative hypothesis, happens to be the same as our claim. And the null hypothesis looks just like that, but we change that greater than sign to an equal sign. So that's what we're looking for in MyLab Statistics. We're going to choose that answer from our list. Okay, so I want the null to be p equals 0.20. Okay, so it's either A, B, or D. And I want the alternative to be that p is greater than 0.20. So there it is, it's B. Great. Now we're asked to identify the test statistic for this hypothesis test. So what that tells me is that they are not expecting us to use the binomial probability distribution. If they're asking us to compute a test statistic, they're asking us to use that normal approximation. So I'm going to do that here. I'll share my paper with you. So we want the value of z. Well, we know that z is equal to the z-score associated with p hat, and that's going to be p hat minus the mean of the sampling distribution of p hat divided by the standard deviation of that sampling distribution. So we want to assume the null hypothesis is true and see that how many standard deviations p hat is above or below the mean, given that the null hypothesis is true. So here's our sampling distribution. We know that the mean of the p-hats is equal to the population proportion p, and if we're assuming that the null is true, we're assuming that that mean is equal to 0.20. Now remember how this works. We studied this back in 6.3. If you're looking at a sampling distribution of p hat, basically what you're doing is you're imagining creating lots of samples of size 233. That's our n value there. And every time you you find a sample of 233 randomly selected subjects, you compute a p hat, and you do that over and over again for different values or for different samples. And then you look at the distributions of the p hats, and we said back in lesson 6.3 that this distribution was approximately normal. And we also said in lesson 8.1 that provided that certain conditions were met, and all of those conditions are met here, the normal distribution is an appropriate approximation to this distribution here. So we're saying, okay, if this is our sampling distribution and this is our assumed mean, where is p hat relative to this mean? And then we're saying, okay, if this is a non-standard normal distribution approximately, what is the corresponding z-score? So if we converted from a non-standard normal distribution to a standard normal distribution, what would that z-score be? Or how many standard deviations would that p hat be above or below this mean? Well, in order to do that, first we need to find p hat. P hat is the number of successes in n trials. And we're calling a success nausea. So you can see this is the number of subjects that experience nausea. Divided by the total number of subjects. You can see that's not actually success, but that's what we're calling success. So success does not necessarily have to be positive here. So we've got 52 over 233. And we can use a calculator to approximate that. I prefer to use that exact answer if I can. So I get about 22.3% or 0.223 as a decimal approximation of that. Okay. So that is our p hat. If this is the mean of the distribution is the population proportion given in that null hypothesis, p hat would be a little bit to the right of that. Or p hat is actually equal to 52 over 233. And the question becomes, how many standard deviations above the mean is that? Well, we can figure out how many standard deviations above the mean that is by computing the corresponding z-score. Z-scores are a number of standard deviations above the mean. So in this case, we'll plug in p hat, which is 52 over 233. And then we're subtracting the mean of the sample proportions, which is assumed to be that population proportion from the null hypothesis. So we're assuming that p is equal to 0.20, and we know that that's the mean of this distribution. And then we're dividing by the standard deviation of that distribution. Provided the null hypothesis is true, the standard deviation is the square root of p times q, that's the complement of p. If p is 20%, q is 80%, we'll write that in decimal form. And then we divide by the sample size, which in this case is 233. So if we compute all of this, we will get our standard deviation, our number of standard deviations above the mean in this case. So I'll do 52 divided by 233 minus 0.2. It's our numerator, divided by square root of p times q, that's 0.2 times 0.8, divided by 233. And we get 0.88. Okay, so that means our p hat is about 0.88 standard deviations above the mean. It doesn't sound too extreme to me. So let's go back to MyLab statistics and see if it likes that answer. So we've got 0.88 there, rounding to 2 decimal places. Okay, great. And now we're asked to find the p-value for this hypothesis test. So again, I'll share my paper with you. And remember, the p-value is, well, it depends on whether the test is left-tailed or right-tailed. It is always related to the area in the tail past the test statistic. And remember, the test statistic actually kind of goes with this picture right here, the sampling distribution. If we take that sampling distribution, which is a non-standard normal distribution, and we standardize it, so instead of having a mean of p equals 0.2 and having a standard deviation equal to this square root of 0.2 times 0.8 over 233, we want our distribution to have a mean of 0 and a standard deviation of 1. And we said in that case, that p hat corresponds to this z-score, our test statistic z, of 0.88. And since this says, the alternative hypothesis says that this is a strictly, p is strictly greater than this value, we can think of that as an arrow that's pointing to the right. This is a right-tailed test. So the p-value in this case is the area to the right of p hat equals this value, which is the same as the area to the right of our test statistic, z equals approximately 0.88. Now that's again using that normal distribution as an approximation. So we'll have p is equal to the probability that p hat is greater than 52 over 233, which is the same as the probability that our test statistic z is greater than approximately 0.88. And if I'm using a greater than sign, I don't have greater than, or I don't have areas to the right in my table. So I need to use areas to the left. The area to the right is 1 minus the area to the left. And we can use either Excel or table A2 to compute this. So I think I will use table A2. So I go to my positive z-scores in table A2, and I'm looking for z equals 0.88. So we find z equals 0.8 here, and then we go to the column where we have an 8 in the hundredths place. So we're right here in this row, this white row. And we're talking about this value right here. I'm going to circle it. I hope that's the right one. So let me use my mouse now. Yeah, so we're in the right column. Make sure we're in the right row. Yes, we were in the right row. So that area is 0.8106. Okay, so we have 1 minus the area to the left of 0.88, which is 0.81. Is that 0.6? Is that what that said? Yeah, I guess it was. And then we'll subtract that from 1 to get the area to the right. And we get approximately 0.1894. Okay, so that is our p-value using table A2. We could have also found that p-value using Excel. So let me show you how to do that in Excel. So in Excel, I would find the area to the left of z equals 0.88 in my standard normal distribution this way. I type equals NORM dot DIST for normal distribution. Open parentheses, 0.88 for my z-score. The mean is 0, the standard deviation is 1. And then we always want to say true to the cumulative part because we're talking about areas to the left when we want the normal distribution. Well, when we are calling this normal distribution function. So we get this value, which is good. That's the same value that we got if we round to 4 decimal places using table A2. That's the area to the left. We want area to the right. So we'll take 1 minus that, and that gives us the area to the right that we got using table A2. Okay, so let's enter that in my lab statistics and make sure that they like it. Okay, so I have 0.1894. says be sure to read the instructions. If there are no special instructions, make sure your answer is rounded to the correct number of digits. Oh, it said to round to 3 decimal places, and I rounded to 4. This is 0.189. All right, great. And then we want to identify the correct conclusion for this hypothesis test. Again, I will share my paper with you. Okay, so our significance level was given to us. It was alpha equals 0.10, and our p-value using that normal approximation to the distribution was approximately 0.189. If I compare those, this is obviously larger than that. So that means that there's a high probability that we would get a p-hat of the value that we got, or a p-hat that's more extreme than that. You can think of it as a probability of 18.9%. So there's an 18.9% chance of getting a p-hat like the one that we got, or one that's more extreme than that, given that the null hypothesis is true. So that's not that rare. 18.9% chance of something happening. Well, that could happen. So if that's not that rare, that means we don't have enough evidence to reject the null hypothesis. It doesn't mean that the null hypothesis is necessarily true. So we're not necessarily saying that the true population proportion is 20%. But we are saying that we don't have enough evidence to suggest that it's not 20%. So here we're failing to reject the null. And let's go back to my lab statistics and choose that answer. Okay, so we fail to reject the null. Okay. Oh, and then it already asks for our conclusion. So in order to decide what our conclusion should be about the original claim, we need to think about the original claim. So I will share my paper with you again. Okay, so we know we're failing to reject the null. Now the original claim was that p is greater than 0.20. So that was the alternative hypothesis in this case. So failing to reject the null is saying, in other words, yeah, p might be equal to 2.0, or 0.2, not 2.0. So the proportion might be equal to 0.2, and that's not consistent with this claim. We're not saying that p is equal to 0.20, but we're saying that it might be equal to that. So I think we can say that there is not sufficient evidence to support our claim. And the claim in this case is that p is greater than 0.20. So there's not sufficient evidence to support that because p might be equal to this value. Now, we don't want to state our answer, or our final answer, in terms of p equals 0.20, because people don't know what that p represents. We always want to go back to the original claim in the problem statement. It said that the claim was that more than 20% of users develop nausea. So we might say that there is not sufficient evidence to support the claim that, instead of writing it that way, more than 20% of users develop nausea. All right, let's go back to our homework. Okay, we failed to reject the null, and we say there is not sufficient evidence to warrant support of the claim that more than 20% of users develop nausea. Great, and that was the end of that question. Now, I would like to show you how to use binomial probabilities to do this one as well. I'm not sure how accurate Excel will be with n equals 233 trials, but I would like to practice at least once. So I'm going to share my screen with you. I'm going to share Excel with you, and then we'll talk through how we would handle this if we were using that exact method using the binomial probability distribution. Okay, with the exact method, we need the number of trials, and that will be the same as the number of subjects. So if we go back to our problem statement, we had 233 subjects. And then we're calling success a subject that develops nausea. In our sample, that was 52 of them. And the p value that's assumed in our null hypothesis is 0.20. So if I want to use the exact method, my capital P value, well, that depends on whether we're doing a right-tailed test or a left-tailed test. Again, the alternative hypothesis was P is greater than 0.20. So that's going to lead to a right-tailed test. Now, if we have a right-tailed test, the P value is the probability that the number of successes is equal to X or greater than X. So we want to know, what is the probability of getting 52 subjects that develop nausea out of the 233 or more, given that the probability of success in one trial is this assumed probability of 0.20. So in practice, what I would need to do is I need to compute the probability of having 52 successes in one trial plus 53 successes in one trial plus the probability of having 54 successes in one trial, all the way through the probability of having all 233 subjects having nausea. Oh, how awful. But in order to find these probabilities, we can use Excel. In theory, hopefully Excel can handle these probabilities with a sample size like n equals 233 or 233 trials. So let's see. Okay, so the first thing I want to do in Excel is I want to create a column for the number of successes. So the number of successes X will be over here. And actually, we know that we only need 52 successes all the way through 233 successes. So I'm just going to start with 52. And then the next number of successes I need is 53. So I'll take that number and add 1. And then just drag and drop until I get 233. This is computationally intensive, so I don't know if Excel can handle it. There, we went all the way to 233. Okay. And then in the second column, I want the probability of X successes in 232 trials, or 233 trials. So these are the probability of exactly X successes. So I need a binomial distribution. So I type equals BINOM dot DIST, open parentheses. And the number of successes I want is this value. So I just select that cell. The next number they want is the number of trials. So it's 233 in our case. And then they want the assumed probability of success in one trial. That's the probability of success assumed in the null hypothesis. So the null hypothesis is assuming that 20% of these people who take this medicine are going to get sick. They're going to get nauseous from it. And then it asks if we want a cumulative distribution or not. We do not want the area to the left of this. What we want is the probability of 52 successes out of 203 trials, not a probability of 52 successes or less than that. So we do not want the cumulative distribution this time, so we're going to say false. Close parentheses, enter, that's giving you that probability. Then drag and drop all the way to 233. And then we want to add those together. Look at that probability of 233 successes out of 233 trials. The 1.38 times 10 to the negative 163. That is a tiny, tiny, tiny probability. But I guess Excel had no problem handling it. So now we want to add all of these probabilities up to get the probability of getting 52 successes or more than 52 successes. Oops. Yep, that's what I wanted. Close parentheses. And we get about 0.2094. Okay, and if we compare that to our alpha value, which is 0.10, p is greater than alpha, so we fail to reject the null. We're saying that if that is the true probability, if the proportion of people that get sick when they take this drug is 20%, then it looks like the chances of getting 52 or more out of those 203 people being nauseous, physically nauseous, due to taking that drug is 20.94%. So that's not particularly rare, so there's no reason to reject this null hypothesis. So we will fail to reject the null. We're saying that the null hypothesis might be true. And that's exactly the same conclusion we came up with up here. Now notice that when we use the normal approximation to the distribution, the p-value was approximately 0.189. When we use the binomial distribution, the p-value was this. So we got slightly different probabilities, but in both cases, those probabilities caused us to fail to reject the null. So we came up with exactly the same conclusion either way. I just wanted you to see that. You can use the exact method if you want to, or if the conditions are satisfied for the normal approximation, you can just use the normal approximation. And I think this time the software, the program, MyLab Statistics, was expecting you to use the normal approximation because they asked for this test statistic. If they hadn't asked for this test statistic, there was nothing in the problem statement to make me think that they wanted me to use that normal approximation. So I could have gone straight for the binomial distribution method if they weren't asking for all of these intermediate steps in the method when they were having you write out your answer or type in your answer. So I hope that helps. See you in the next video.